We will learn about the way to solve problems from the accelerating frame of reference or the non-inertial frame of reference. Now, as we have learned that Newton's law is not valid for the accelerating frame of reference. Okay. Now, let us take two observers. First observer is on ground. Let the name be G. Second observer be O, and this is a moving observer. Say this is having an acceleration AO, and this is a particle P. Particle P having an acceleration AP. Right? So the G is the inertial frame or the ground frame. Now O is the accelerating frame or the non-inertial frame, and this P is the body of mass m. Now this AO is the acceleration of O. AO is acceleration of the observer or the frame O. Now see, acceleration of G is 0. Now AP is the acceleration of P, obviously with respect to ground frame. Any absolute acceleration with respect to ground frame. Suppose this AO is also with respect to ground frame. Now we know the equation of relative acceleration, but for that I have to draw the diagram again. This is O having acceleration AO, this is the particle P having acceleration AP, and this is the observer on ground. Now by the equation of relative acceleration, we know that, see, acceleration of P with respect to O is acceleration of P with respect to O, denoted like this. So it is acceleration of P minus acceleration of O. This is what we have learned from the equation of relative acceleration. Similarly, a relative velocity would be like this. Velocity of P with respect to O is velocity of P minus velocity of O. Similarly, this is the equation of relative acceleration. Now then this m is mass of this particle or the body P. So multiply mass on both sides. So m AP with respect to O equal to m into AP plus minus m into AO. Now according to Newton's law, what is the force acting on P? See, Newton's law says that force equal to mass times acceleration relative to the ground frame. So this term is the force F, that is the force on P. This is the absolute force on P. Now what about this? This is mass times acceleration of P with respect to O. Now if you solve the problem with respect to O, then mass into acceleration of P with respect to O is this force plus this extra term. Now this extra term is known as pseudo force. Pseudo means fictitious force or false force. This is not a force actually, this is a correction factor. This is used if a problem is solved with respect to an observer who is accelerating. So this is mass times acceleration of P with respect to O. is actually the true force plus pseudo force. What is the pseudo force then? The pseudo force is equal to minus of mass of this object times acceleration of the observer. So there is a minus sign here. Now we'll see how to apply this concept to solve problems. Now let's go back to a previous problem, very simple problem. That's I think in the first or the second lecture we have discussed this. A person of mass m inside a lift accelerating up at rate a, at acceleration a. Now find the normal reaction or apparent weight, whatever you say. Find the normal reaction of lift floor on the person. Yeah. So this was the case, very simple. This is the person, looks like a ghost, I can't help. So this is the acceleration A. Now what we have done, we have drawn the free body diagram. So this is, what are the forces? The force is mg, and then the normal reaction, this R for the normal reaction or apparent weight. Now due to these forces, the combined effect, it is having an acceleration A. So we simply apply Newton's law, the net force. So we have to choose the direction upward positive, right? So net force, so R minus mg equal to m times A. So R equal to m times g plus A. This is what we had done before. Now we have solved this problem from a ground frame actually, right? So this problem has been solved by this G, someone standing on ground, because someone standing on ground will see this person accelerating upward with the same acceleration as that of the lift. Now this same problem I will solve it from within the lift. Okay, so from within the lift someone has to solve the problem. The person can himself or herself can solve the problem, or you can place one more person inside the lift. So I am looking at this person who is solving the problem. Okay, so according to the person himself is at rest, right? Relative acceleration. See, if I name this person as say O, person has name O, right? Or I mean O for observer. So what is the acceleration of O with respect to O? 0, obviously. So with respect to this person himself, he is at rest. Now let's see what are the forces acting. So mass into acceleration of O with respect to O is 0. Therefore the net force will be 0. So there is an extra force, right, with respect to the frame O itself. So these are the real forces. Real forces are mg, R, and what was the force? The term which is not really a force, but it is a correction factor. To solve problems from the accelerating frame, we need this pseudo force. What is its value? Minus m into AO. M is the mass of the observed and AO is the acceleration of the observer. Okay, remember that. P is observed, O is observer. this is mass of P, this is acceleration of O. Now here the observer and the observed are same, so minus what is the pseudo force? So the acceleration of the observer is upward, so this is the pseudo force. Generally we denote the pseudo force by a dashed line because it really doesn't exist. The thing is that Newton's law is not valid with respect to the accelerating frame of reference. We are making it valid by bringing in the pseudo force. So to cancel one wrong, you bring in one more wrong thing. However, a bit more practice on pseudo force will clear up your concepts. So this is M into A, downward. Why it is downward? See, vectorially what is pseudo force? A is equal to minus mass of the observed times acceleration of the observer. So the observer has acceleration A upward and mass is M itself. So there, to keep in mind this minus sign, that means the force acts downwards, opposite to the direction of the acceleration of the observer. So this is a pseudo force. And with respect to this person himself is at rest. So we will just balance the forces. So MA plus MG is equal to R. So R equal to M times G plus A. Simple as that. That is what we got by the last method. If you solve from ground, or you solve from within the lift, you will get the same answer. This could have been solved from within the lift, right? Same thing. Just suppose you make one more observer, this little boy, gazing at this person, right? So make this O and make this person P. So as you know that M acceleration, mass into acceleration of P with respect to O is force plus minus MA. So here the acceleration of P with respect to O is how much? 0, obviously, right? Both are inside the lift. So now this force, what is the force on this person? This accounts for the real forces. So mg and r, real forces done. Now minus m into AO. So this observer is having acceleration upward, AO, so pseudo force will be downward. So m into A, right, downward. So this is 0 with respect to O. P is having no acceleration. So this left hand side is 0. That means the forces will balance. Okay. So that means R equal to M times G plus A. Now let's solve some more problems we have done before. Those type of problems we can solve. Say, if you remember, in some lecture I have discussed this problem. There is a smooth incline and there is a block on the incline, right? This is having acceleration A. Now for what acceleration A of the wedge, the block does not slide relative to it. Now all surfaces are smooth. Okay. Now, though we have done this before from ground frame, still I'll show you again how to solve it from ground frame. Now this is the block. Now this little g is standing on ground and observing the whole thing. Solve from ground frame. So it's solved from ground frame. So from ground frame, this is having acceleration A, and let's look at the forces. What are the forces acting on this block? The forces is mg and the normal reaction. That's it, nothing else. So due to the combination of this, so this is so take this as the x-axis, this as the y-axis. So this is r cos theta. Remember, this is theta, then this is also theta. Don't make it 90 minus theta. And you know the trick, right? How to avoid the mistake. Okay, right. So along y-axis and along x-axis. So in y-axis, see, this has been resolved. So just cross it. So along y-axis there is no acceleration. So r cos theta is equal to mg, and along x-axis r sin theta equal to ma. So if you divide this two equation, you get a by g equal to tan theta. Therefore a is equal to g tan theta. Fair enough. Now we are going to solve the same problem from an accelerating frame of reference. In some situations, it is absolutely necessary to solve problem from the accelerating frame of reference. That is why you may be thinking that, okay, this problem is solved, it's done. So why even think about the accelerating frame? It's done already. No, you got to have all the weapons with yourself. Never know which one works at which situation. Okay. So here the observer is there, right? Observer, he's sitting on this. So this solve with respect to the wedge. Solve with respect to the wedge. That means this person, see, the wedge doesn't have eyes, so we make this person sitting on the wedge, right? So this person, so according to this person, this block is absolutely at rest. Now the wedge has acceleration A, so this observer O has acceleration. Now this is a particle being observed P. So let's look at the forces. This is mg, this is r, and from the wedge frame, what is the pseudo force? This way. This is the pseudo force. And with respect to O, P is at rest. P is absolutely at rest or in equilibrium. So that means these three forces cancel. These three forces will balance to give resultant force 0 with respect to this person, remember, not with respect to ground. So let's resolve this. Theta, so this will be r cos theta, this will be r sin theta. Just cancel, just cross off this one, right? So this, so you can draw this x and y axis. So in x axis r sin theta equal to ma, in y axis r cos theta equal to mg. See here see from the ground frame also this was the same equation, r sin theta equal to ma, but the meaning in this case is very, very different. Here r sin theta and ma balance each other. This becomes the pseudo force. And in the last approach from ground frame, it was pretty different. Okay, so just to divide and get a equal to g tan theta. Now this problem, now you will feel why at all this pseudo force approach is needed when you solve this problem, right? Okay, let's make this height h. Okay, now this block is here, just at this end. Now the wedge starts to move to the right with an acceleration of a equal to 2g tan theta. Find the time required by the block to climb to the top of the wedge. See, in this case the acceleration is larger than, and it's actually twice of g tan theta. If you move up g tan theta, then this block will just stick to the wedge, right, and it won't move relative to the wedge. Now this situation is very, very different, and not to always you should mention that all surfaces are smooth, because we have not learned friction, and surfaces are smooth also. Right, so this I'll solve from the frame of the wedge. Solve from frame of wedge. This is a block, and let's see what are the forces on the block from the wedge frame. See, make this is the symbol, that is the wedge frame, right? Wedge frame, that is, this is O, and observer, or say the wedge's eyes. Okay. Now what are the forces? mg and normal reaction r, and as the acceleration is this way, so will be the pseudo force towards the left. Oh, this should have been a dotted line. Okay, never mind. A firm line will also do. So pseudo force is m into a, that is m into, so a is 2g tan theta, so 2 mg tan theta. This is the pseudo force. Now if you look from the wedge, obviously the block will slide here with respect to the wedge. So here, so this is I make it acceleration a dash. So a dash is acceleration of the block relative to the wedge. Acceleration of the block relative to the wedge. Okay. Now, so this has to be the x-axis and perpendicular is the y-axis. So let's resolve the forces quickly. Okay, this mg will be resolved into mg cos theta, and this will be mg sin theta. If you want, you can draw a free body diagram, totally this block separated from this wedge and everything else. Okay. What about this? 2mg tan theta multiplied by cos theta. So that's 2mg tan theta multiplied by cos theta means 2mg sin theta, and this this is 2 mg cos tan theta multiplied by sin theta. Okay, so 2 mg sin square theta by cos theta, whatever. So we are not worried about this y-axis, but we are worried about a dash, so these two forces will do. So again, from the frame of the wedge, these are the forces. So the net force in these directions, so that's 2 mg sin theta minus mg sin theta. So this is mg sin theta, and these are this normal reaction, component of this, component of that. This doesn't matter, right? So this is the acceleration a dash of the block relative to the wedge. Okay, so from the wedge, what we can write? From the wedge frame, we can write m times a dash. See, it is this. See, a dash is, see, remember this, m times ap with respect to O is force plus minus MAO. So these are the real forces, right? This, and this one was there. So m into a dash is actually the sum of the real force and the pseudo force. So there it is. So we are applying it along the x-axis only. This is what matters. M into a dash is equal to mg sin theta. So therefore a dash is equal to g sin theta. So the time taken, so this height is h, so this length is h by sin theta. So we can write h by sin theta. Now with respect to the wedge, this block starts from rest, so half a dash times t square. So therefore h by sin theta equal to half g sin theta times t square. So therefore t equal to 1 upon sin theta, here 1 upon sin theta root over of 2h by g. Again, this problem is quite an easy one. So this is a cart, and inside the cart from the ceiling there, this thing is hanging, a ball hanging from a string. So you have to find this angle theta. This cart is having an acceleration a, and this is vertical direction g. So the cart moves along horizontal with an acceleration a, Now at steady state means just when this was vertical, car starts, so it will move around and oscillate. I'm not talking about that. At steady state, right, this it makes a constant angle theta with vertical. At steady state, find the angle made by the string with vertical. See, this problem I'll solve from two frames. One is a ground frame, another a person. O will be inside the cart. So solve with respect to G. From the ground frame, what the person will see, what are the forces? Mg and this is the tension T, and due to this net effect there is an acceleration A. So this theta, right? So that's T cos theta, this is T sin theta, okay, and let this be x axis, this be y axis. So T sin theta is equal to ma and T cos theta equal to mg. So therefore tan theta is equal to a by g. So theta is tan inverse of a by g. This is how we find out by solving from the ground frame. Now I'll solve it from the cart frame, that is person moving in the cart, inside the cart. When he or she looks at this, then with respect to O, this is absolutely at rest. So these are the forces. So the sum of all forces is 0. I mean including the pseudo forces. So that's it. This is should be a dotted line. Never mind. So MA. Right. So T here, angle theta, mg, and this is ma. So the with respect to O, this is the free body diagram of this ball, and the net force is equal to 0 because the ball is at rest. So how is the net force 0? Then you have to resolve this. T cos theta, this is T sin theta, and x and y axis separately. So T sin theta equal to ma, forces balanced in x axis, and T cos theta equal to mg, forces balanced in the y axis. So tan theta is equal to a by g. By the way, out of the context, you can solve it by the famous triangle law also. There you have you are lucky to get 3 forces here, and pseudo force as you are solving with respect to O, an accelerating observer. So the sum of these 3 forces is equal to 0. So place them one after the other. They will form a closed triangle like this. T, ma, put it here, and mg, put it here. 1, 2, 3. The vector sum is 0. And see, this is a right angle triangle. So ma by mg is equal to tan theta. So tan theta is equal to a by g.